So dear students, I welcome you all in this class on analog and digital communication lab. So we have completed 4 experiments till now, and today we will demonstrate 2 experiments, experiment number 5 and 6, which involve PWM, that is pulse width modulation, and PCM, that is pulse code modulation. In the theory class also we have discussed the concept of pulse width modulation, and today's lab experiment demonstration will further concretize your concept on PWM and PCM. So now let us start with your experiment number 5 first, that is pulse width modulation. Miss Ankita, you please continue.
Thank you, sir. So first of all, I welcome you all. Today we will do 2 experiments, pulse width modulation and pulse code modulation. Uh, Pulse width modulation is analogous to the pulse in 3 types of pulse modulation techniques we have learned so far: pulse amplitude modulation, pulse width modulation, and pulse position modulation. I have explained you in the previous lab that according to the characteristics variations of the pulses, we can modulate our pulses in the 3 ways: either through amplitude, through time duration, or through starting position of the pulses. Today we will learn about the pulse width modulation and demodulation techniques using a trainer board. uh, Pulse width modulation. So what is a pulse width modulation? In this technique, we will vary the width of our training pulses, or we can see our carrier signal. The width of the carrier signal is varied according to the amplitude of the message signal at that instant. At a particular instant, what is the amplitude of message signal? According to that, the width of or the broadening of the pulses will occur, either broadening or we can say shrinking of the pulses. According to the amplitude of the message signal, this broadening and shrinking of the pulses and in the time domain, in the time duration, this technique is called pulse width modulation. But in the pulse width modulation, the width of each pulse will be proportional to the amplitude of message signal at that instant. But the amplitude of the pulses will be fixed, and the starting time of each pulse will be fixed. Uh, you can thus the time duration will vary, and this transmission technique is also a baseband transmission technique. Baseband transmission technique means low frequency transmission techniques. These signals will not be transmitted through a wireless channel. These signals will be transmitted through a wired communication link, and the message signal will be analog. The carrier signal will be in the form of pulses. And this is not a purely digital modulation technique, because the variations in the pulses, either in amplitude, either in time domain, or in the phase domain, or we can say position, will be continuous in nature. It will not be a discrete form. So we can say this is not a particular digital modulation technique. These techniques are termed under pulse modulation technique, and here pulse width modulation will be discussed. Pulse width modulation generation. How to generate a pulse width modulated signal? How, or we can say how to vary the width of the pulse in accordance with our message signal. So there are 3 methods. First, using a comparator, and second one is using a monostable multivibrator, and third one is using an IC555 timer. So using a comparator, a signal will be the modulating signal value is compared with the carrier signal, but the carrier will not be in the form of pulses. Here the carrier will be in the form of the sawtooth waveform, or we can say ramp signal, uh, a sequence of ramp signals where the modulating signal amplitude is compared with the sequence of ramp signal, and the output of the comparator will be in the form of the pulses with the duration of the pulses varied in accordance with the modulating signal. Pulse width modulation can also be termed as the pulse time modulation, pulse duration modulation, or pulse length modulation, because the time duration of the pulse is varied or the length of the pulse occurring is changing here. Second one is the using monostable multivibrator. Um, Till now, you may have learned about this term monostable multivibrator, or will learn it in future in your analog subject. But this do monostable multivibrator is a technique which have only one stable state, and the uh, only one stable state, either 0 or 1. And when we will trigger it with an external triggering signal, it will go into unstable state. If it is in earlier in 0, then it will go to 1. If earlier it is in 1 state, it will go to 0. That means the state will be changed by triggering of the pulse. It will never go into the continuous formation of the pulses. Or using IC 555 timer. Again, IC 555 timer will work in the monostable state. Uh, you can see this. If the monostable state is working in the one, uh, the stable state is 1, then if we trigger the pulse, then it will go to the 0, and then if you again provide the triggering pulse, it will go to 1 and then come down to it, comes back to its stable state. That will it will go into its stable state for once when we triggered it. Otherwise it will stay in its stable state, either 0 or 1. 555 timer is an IC which can work either in unstable mode, stable mode, or bistable mode. These three states are present for a multivibrator. So here we will work as a monostable state. Modulating signal in the multivibrator or IC 555, the carrier will be in the form of pulses, whereas in the comparator circuit, the carrier will be in the form of this ramp signal. So here you can see the pulse width modulation generation using a comparator circuit. First, here is an input is given in the form of sinusoidal signal, or we can say message signal is in analog form. Second one is the carrier signal, which is in the form of ramp signal, or the sequence of the ramp signal. Here a comparator is given, and the comparator will provide the pulse width modulation. Here PWM will come. So how does this work? You can see in the second graph, when the amplitude of the message signal is higher than the carrier signal, the comparator will provide a positive output. You can see that when the message signal amplitude is higher, a particular threshold level is set here, and when the message signal is higher than uh, the carrier signal, the comparator output will be high, and when the message signal output is less than the carrier signal, the comparator output will be low. And the demodulator circuit in this graph, the demodulator blocks are presented here. First, the demodulated circuit. What will a demodulator will do here? Just like in the FM, we have converted the frequency variations in the form of the amplitude variations, and then envelope detection was done there. Similarly, pulse width modulation is analogous to FM. So what we will do in this is demodulation. We will convert the variations in the time duration of the pulses in the form of the amplitude of the pulses. The this demodulator circuit will do that, and then the sample and hold circuit will hold the sample variations, and then this amplitude variations will be passed through a low pass filter, just like we have done in the pulse amplitude modulation, where an envelope detection was done followed by a low pass filter. So the same work will be done here. Firstly, we have to convert the pulse width or pulse time variations in the form of the pulse amplitude variations, and then the pulse amplitude variations will be converted, will be detected through envelope detection and the low pass filter circuitry. Second methodology is using IC 555 timer. IC 555 is an 8-pin IC whose working, or we can say whose connections are mentioned here. This is the out. This is the front front panel type view of IC 555. And how does this work? At this second pin, triggering of the clock signal. Here the trigger signal will be given instead of the clock signal. The trigger signal, firstly clock signal will be given to a differentiator, and the differentiator will generate a triggering signal. Triggering either positive triggering or the negative triggering. Triggering is a kind of impulse signal. It is a very short duration signal, and then the modulating the signal will be given at this fifth pin, and the output we will get through this third pin, and the output will be in the form of pulses whose width will be in the varying form. You can see that monostable multi-vibrator waveforms. Firstly, it was in the stable state. Stable state was its plus VCC. Then it was triggered, and the negative triggering comes, and then the capacitor starts charging and then when how much time capacitor will charge, it will be decided through a comparator which will compare the VCC signal with the modulating signal, and this then the capacitor then when the comparator output is higher than the VCC signal, the capacitor will charge, and after this when the modulating signal output will be lower, then the comparator output will be low and the capacitor starts discharging and our pulse will go down. So the generation methods have been discussed till now. Now we will discuss about the waveforms, how waveforms will be generated, or what type of waveforms will we will observe on a CRO when we perform the experiment. First waveform. Here shown the PWM generated signal. Here the message signal is provided. A message signal is in negative. The width of the pulses is very narrow. The amplitude of the message signal is increasing. The width of the pulses is increasing. Similarly, we can say the same pattern. As the message signal amplitude increases, the width of pulse increases. And as the width of message signal, as the amplitude of message signal decreases, the width becomes narrower. And I have this was the PWM output from a comparator circuit. And when we will demodulate our pulse width modulated signal, it will pass through a demodulated signal. You can see that a PAM signal will be generated through these pulses. The pulses width variation will be converted into amplitude variation, and then these amplitude variation will be provided to a sample and hold circuit, which will hold that particular sample for the entire duration, for the entire pulse duration. And then this sample and hold circuit shown in the form of blue signal is provided to low pass filter, and the last red color signal is the low pass filter output, which is similar to our transmitted message signal. There is some delay in the transmitted message signal. You can see that the starting of and the ending of the message signal is not same at the modulating and demodulating that. This was due to delay in the particular blocks of our modulation and demodulation circuitry. So here you can see the pulse width modulation and demodulation using a comparator circuitry which we had discussed earlier. So here is the trainer board PWM experiment.
In this kit, we have a pulse width modulator block whose input is given at this terminal. The input may be taken as sine wave, square wave, triangular wave, or any wave, but we have selected a sine wave. At this point, the carrier signal is internally fed, which is a triangular wave. We obtain output at point number 11, and in this way we can observe various waveforms at various ports. Let us observe waveforms. At point number 9, the message signal is displayed like this, and at point number 10 we have a carrier signal, which is a triangular waveform, is shown here. The output of the pulse width modulator can be seen at point number 11, which is displayed like this. You can observe that the width of the pulses are varying in accordance with the master signal. So in this way we have observed pulse width modulation. Till now we have observed output of the PWM modulator. Now we'll observe what is the output of PWM demodulator. For that we connect CRO probe at the output of the PWM demodulator, and which consists of a demodulator, sample and hold circuit, a low pass filter, and the output is displayed at the DSO, which is this one. This is the output of PWM demodulator, which is a replica of original master signal. So in this way we have obtained our original master signal by performing PWM modulation and demodulation. Thank you very much.
So now we have learnt about this pulse width modulation and demodulation technique. Here is our sixth experiment. Here it will the pulse chord modulation will come. Pulse chord modulation, demodulation. Earlier we have seen the three pulse modulation techniques, that means pulse width modulation, pulse amplitude modulation, and pulse position modulation. All these techniques were analog transmission techniques. That means the continuous variation. So we have done pulse amplitude variation. According to the message signal, the continuous variation in the amplitude of pulses was there. If we have seen the pulse width modulation, the continuous variation, or not a particular fixed value, any value variation we have seen in the pulse width. And if we check the pulse position modulation, and we can see the starting position will also be a continuous in nature. But here a new type of modulation technique comes, that is pulse chord modulation. Pulse chord modulation in this pulse chord modulation output, the digital signals will be generated. This is a kind of analog to signal generation and modulation technique. Here ADC, or we can say analog signal, will be transmitted to the digital signal. This is specifically a digital modulation technique where the digital signals will be generated at the after the modulation. Here the amplitude of the sampled waveforms at the defined intervals is represented as a binary code. What does this mean? You can see this in waveform. A waveform is the analog waveform is our message signal. The message signal will be converted into this one sample of the message signal signal will be converted into a specific number of bits, and the other sample will be converted into a bits. And this shows that the sample and a particular sample of a message signal is converted into form of the number of bit sequence, or we can say bit sequence is termed as a binary code. The message signal is converted into a binary coded signal. So earlier pulse modulation techniques, PAM, PWM, and PPM were mainly not a digital. We can say these are pulse modulation techniques, not truly analog, not truly digital. They were pulse modulation techniques. But this PCM signal is termed as a pulse code modulation is termed as a digital modulation technique. Here, analog signal is converted into a digital form, and again, this is also a pulse modulation. So the transmission will not be through a wireless channel. Again, the transmission will be through a wired channel, communication wired link or a basement channel. The PCM signals are transmitted. So here is the block diagram of the PCM transmission and reception, how PCM signals will be transmitted and received that are shown here. First, analog message signal will be generated here. Then it will be passed through low pass filter. What does this low pass filter, the transmitter, do? It will band limit our transmitted signal to a particular range of frequency. Like if our, for example, we can say our message signal frequency is FM, but sometimes noise occurs and the signal frequency increases from FM. The signal frequency expands from the FM. So low pass filter will limit our signal to FM frequency. Then the sampler. What does the sampler do? It will provide the samples of our transmitted analog signals. How the samples will be generated, we have discussed in pulse amplitude modulation. It will be a sample and hold circuit here, which will provide the sample and then holds that value of the sample for the entire pulse duration. Sample and hold circuit will work will in this similar way as in the pulse amplitude modulation, or we can say pulse amplitude modulator is placed here. Then this signal will be transmitted through a quantizer. What does this quantizer do? We have collected the samples of our signal. The signal samples are, first sample say is of 0.7 volt, second sample is of 1.9 volt, third sample is of 3.3 volt. Then a particular levels will be set. These different values or because these sample values will be continuous in nature, they will be of infinite range. We can say very large range of the sampled amplitude will be present. So we will limit that amplitude. We will provide a fixed amplitude signal. We can say we have a 1.9 volt will be set to 2 volt. The nearest value, nearest level we have set that this particular quantizer level we have set will be set here. You can see in this signal the stage 1. In this diagram, the stage 1 shows the sample and hold output. Sample and hold output, as we have earlier discussed in the waveforms in our pulse amplitude modulation experiment. And then these signals will be assigned a particular value. For example, these levels are set here: 0, plus 15, plus 60, plus 85. The particular sample values will be set here. And this after quantization process. In the quantization process, for example, we have taken 0 to 8 volt and we have set 4 levels: 0 volt, 2 volt, 4 volt, 6 volt. These are the levels we have set, and all the signal amplitude will be converted into these levels. What will be nearest, the values will be assigned to that level. And then after this, we have now 4 levels: 0 volt, 2 volt, 4 volt, 6 volt. These voltage levels will be converted into, will be provided to an encoder which will encode these signals. 0 volt encoder will provide the bit form to these signals. How these signals will be converted to bit form? For example, 2 volt signal sample coming here, then 2 volt signal will be, for example, we are using 4 bits. 0010 as an coding will be provided to that 2 volt, and for 4 volt 0100 will be provided to that volt. Similarly, the encoding will be done that will provide the bit form or the binary values to our quantized level. And how these bit the number of bits will decide about the quantization level. How many number of bits we have set here, and the quantization levels will be setting according to this. For example, we set 2 bits, quantizer level will be 2 raised to power n. N is the number of bits. So n 2 raised to power 2, that means 4 quantization level will present. We in this particular experiment we will perform here, we will show the demonstration. 7 bits are used. So that means 2 raised to power 7. That means 128 quantization levels are set here. Uh, and this up to encoding. This was the work of analog to digital conversion, and in the PCM modulation system, in addition to encoding, a particular line encoding is done. For example, you can see in this diagram, this was the sinusoidal modulating signal. The bit sequence assigned to a particular sample of the signal is presented here uh, according to the quantization level. This was the quantization level 5 volt. Then this number of bit sequence is provided to this sample, and thereafter for this sample this bit sequence is provided. This was the digital form of our transmitted signal, and this signal is in logical form 1010. 10 cannot be transmitted directly, we have to provide it in electrical form. Only electrical signals will be transmitted either through the transmission channel. So this conversion of logical form into electrical form is called line coding. 1010 is not a particular sequence we can transmit directly. We have to provide the electrical form, or we can say voltage levels to our particular bit sequence, and then transmit it through the channel. There are some line coding example: unipolar energy. Energy means no return to zero. For entire pulse duration, this signal will be provided into a fixed voltage, but it will never comes to zero for entire pulse, for entire bit duration. Polar energy, no return to zero, but earlier was unipolar. Either plus voltage, only positive voltage will occur in unipolar. In the bipolar, or we can say polar, positive and negative voltage. For the zero, negative voltage will be taken, and earlier in the unipolar, for the zero, no voltage was transmitted. Similarly, bipolar encoding. These are some examples. So you will learn in your theoretical classes that what types of linear encoding are there and how this is done. I have shown you some just examples here, that the logical signal will be converted into electrical signal. If we have done, for example, NRZ, and our sequence was 1010, then we will provide 5 volt for 1, 0 volt for 0, 5 volt for 1, 0 volt for 0. That means 1010 is converted into a voltage form. And after this, a regenerative repeater. Regenerative repeaters, when we have to transmit a longer distance, when we have a long we have to transmit our signal through the long distances. The digital signal have the high probability of distortion. The bits generated are distorted, so we have to use regenerative repeater. What it will do? It will generate the exact replica or the exact fresh copy of our transmitted PCM signal. The same transmitter section will be provided here, and it will again generate this PCM signal and then transmit And then again, depending on the distance, we have to use the number of regenerative repeaters. For the short distance transmission, this regenerative repeater is omitted. And at the receiver side, again, this encoded signal will be decoded. The bit sequence will be converted into quantization levels, and the sample and hold circuit and reconstruction filter will detect the sample and hold circuit, hold signal, sample and hold signal, and then it will be provided to the destination or the at the final receiving side. So this was the again a PCM generation which we have discussed earlier in the previous slide. Again shown here. First step is the sampling of the signals, sample and hold circuit. Whole signals will be shown, and then the quantization level will be provided, and then the signal, these quantized levels will be encoded in the form of the bit sequences. Now these two signals are shown for if we have only a straight line signal, then this type of A&DC output we will get. And if we have sinusoidal signal, this is the representation of the signal. Actually, this is not the exact representation we will get in the CRO. This is just the visualization of the our signal, that for a simple sample, we have got this bit sequence. We will observe only the bit sequence 0, 1, 0, 1. According to the levels we will observe on CRO. This is just the visualization to specifically show that how this signal is converted into a digital form. Time division multiplexing. In this experiment, a time division multiplex circuit is also present. What is the time division multiplexing? Multiplexing you have learned in the digital electronics subject. What does a multiplex do? It will take the signals from the different inputs or different generators and multiplex into a serial form. The parallel signals are converted into a serial form. It will provide a particular sequence to the signals. In the time division multiplexing, what will be the sequence? Sequence will be in the form of time. A time frame will be considered, for example, 0 to 10 seconds. 0 to 10-second duration signal, and this signal, this duration signal is converted into, for example, we have 4 transmitters. So it will become chopped into 4 blocks or 4 frames. One duration signal is called that one TDM frame, and 4 slots will be provided, equal slots will be provided to each channel, and then this signal will this first slot will be provided to the A transmitter, second to the B transmitter. This similarly, the TDM signal will be passed, and at the receiving side, demultiplexer will use, and that demultiplexer signal will pick up that signal from a particular slot. It will and then provide to that particular receiver. The frames will be converted into the slots. For example, 4-second frame we have used, 0 to 4-second frame we have used, and for 0 to 1 second, A signal will be transmitted, 1 to 2, B will be transmitted, 2 to 3, C will be transmitted, and 3 to 4, D will be transmitted. Thus, the time division multiplexing will work. This is a principle of 4-channel TDM system. Channel 1, 2, 3, 4. And this is a switch. For first time slot, switch will be connected to channel 1. Second time slot, switch will be connected to channel 2. Similarly, for the 4 time slot, the switch will be connected to different channels. And similarly, at the transmitter side, the switch will the switch position will change according to the time slots. And this the time division multiplex signal is shown here. So
which is used in our laboratory.
this
So
is
this
the
is the
video demonstration of our PCM signal. Just I have giving you a briefly review what we will do here. Here the LEDs are present. What does LED will provide? LEDs, I have said that the 7-bit coded signal will be generated in this experiment. That means 7 LEDs are present. For example, any sequence will be generated in the form of 1010 form. The particular LED will glow. Here is the LSP, here is the MSP, with the LEDs here, you can see that error check course generator. Error check course generator means the parity. You have I learned about the parity. You have listened some parity word. Parity is an error checking code. Similarly, having parity codes are present in this script. We can use any error checking code here and observe the output. And these LEDs will show that particular bit sequence. And time division multiplexing, two channels are provided for the multiplexing in the time division signal form. And for the transmission and reception, two different bits are there. And rest you will learn in this video.
TDM, PCM transmitter trainer. So it is mentioned that it is a TDM. That means we can also do some multiplexing in the PCM system. But of course you can do. But first we take the PCM system with a single input. Later we can do multiplexing if required. So in this particular PCM transmitter diagram, this is entirely PCM transmitter only. There is a separate hardware kit for PCM receiver. So in this PCM transmitter, let us observe in the function generator we have 4 different input knobs. 2 signals are nothing but, 2 knobs are nothing but DC1 and DC2, that is DC signals, and other 2 signals are AC signals having some sinusoidal frequency of 1 kHz and 2 kHz. I will explain why the DC signal and the AC signals are separately given in this experiment. Now, this part is nothing but the complete transmitter part of the PCM system. So in the transmitter only, sampling, quantization, encoding, all the 3 blocks are there. Okay. Now, for example, if you want to convert the analog signal, sine wave analog signal to digital signal by using PCM system, and also if you want to observe what is the PCM output, then select any of the sinusoidal signal from 1 kHz or 2 kHz. So here I'm selecting, let us select a 1 kHz signal and connect this 1 kHz signal to the transmitter input. Okay. Here there is another channel. Why there 2 channels are given? That means for the purpose of multiplexing, if you want to multiplex 2 signals, this is the another channel. But if you don't want to multiplex, you want to convert this only 1 signal to PCM output, then you can use only 1 channel. Or else you can connect these both the channels to same way, so that from these 2 channels only 1 signal is transmitting finally. Okay. Now after connecting this sinusoidal signal, first you need to observe what is the sinusoidal signal coming in the CRO and what is the amplitude and frequency, then only connect this to input. Then here carefully observe again, as like in time division multiplexing, again there is a clock or a sampling clock here. If you observe at this point, there is a clock signal is obtained, and the same based on this clock signal the input is sampled. Whenever if you observe this kind of switch, that switch is nothing but a sampled switch. So based on this switching operation, the analog signal is going to be sampled based on this clock pulse sampling rate. Okay. So when the switch is open, no signal is transmitted. When the switch is closed, only the sample of the signal at this particular instant is going to transmit. Like that, after this point, sampled signal is obtained at this particular pin. Similarly, if you connect another signal, the sample signal is coming at this point. So finally, if you observe at this particular point, sampled signal is obtained. Similarly, this block represents the quantization process. Inside that there is a IC diagram for quantization, but that is not shown. So here, after this particular pin, if you observe this pin connected to CRO probe, then if you observe in the CRO there is a quantization output. And then where the encoder is, this particular block represents the encoder block. This particular block represents the encoder. That means if you apply this quantizer output to the encoder, so this encoder will assign each quantized amplitude value into some group of bits. Here, how many group of bits are used for each sample value? Total 7 bits are used to represent the quantized value. Here, in order to understand or in order to enable number of bits, here these LEDs are used. Whenever the LED is on, that means here binary 1 is on. Whenever LED is off, means binary 0 is on. Like that, you can clearly observe what is the bit sequence or what is the group of bits assigned for each quantized value or each sample value. So that we can observe directly, and all this bit sequence is applied to output logic, and finally if you observe at this particular point, that is the PCM output. So this PCM output, if you observe in the CRO, then this bit sequence, that is binary ones and zeros, are converted into electrical waveform. You observe this electrical waveform is obtained. Is that clear? In this way, we can convert this analog signal to sample signal, quantized signal, and then digital signal. Okay. Now, and also where the clock pulse is there, this is where the sampling clock we can observe. Right. Now we'll see how the different signals are obtained in the CR. Of course, this is the received hardware kit, and this is especially for PCM receiver kit. After obtaining the PCM output, if you connect the PCM output to the receiver input like this, then this is the complete PCM receiver block, which contains the reconstruction filter, digital analog converter, and filters, and low pass filter. After this entire process, finally we observe the CRO probe at this particular point, then directly the demodulated signal, that is what the original sinusoidal signal we have applied as the input in the transmitter, the same signal will be obtained here. And also in the PCM receiver, we can also observe that whether the binary bit sequence is perfectly decoded or not in this particular D2A converter. If you observe in the D2A converter, whatever the bit sequence there in the transmitter, the same bit sequence is decoded here. That you need to observe, and then only that is converted into original signal. Okay. Now we'll see all these operations one by one. Actually, I have already explained this procedure. Now, if you see, I have taken 1 kHz as a input signal, and that input signal is connected to here, and both the channels are combined because we are using only one signal, not a multiplexing signal. So, if you connect this input to the CRO, so this is the positive pin and this is the negative pin. Okay, that is connected to ground. So, if you connect this to CRO, then you'll observe there is a sinusoidal signal in the CRO screen. We can take either 1 kHz signal or a 2 kHz signal, whatever. Next, where the clock pulse is there, we already know that here this point we have a clock pulse. If you observe this here at this particular point, you can also observe the clock pulse or a sampling clock. Only based on this sampling rate or sampling time only, the sample signal will be generated. Next, if you observe the CRO probe at this particular point, then you can clearly observe after this sampling process, the sampled signal will be obtained like this. If you can clearly observe the CRO screen, there is a dotted line of sine wave is obtained. Each dot represents the one sample value from the input analog signal. Similarly, if you zoom that sample output in the CRO, so it will be obtained like this. So these are first sample, second sample, third sample, like that. Okay, all these vertical lines represent the clock pulses. Based on the occurrence of each clock time, different samples are obtained like this. Okay. Similarly, if you observe the quantized signal, both sample signal and quantized signal look like the same, but here if you observe that the sample signal may have some curvature outputs, but the quantized output is having constant output. Only the difference between sample and quantized signals are the sample values are going to be approximated to nearest quantized levels. Here there may be some approximation. All the sample values are approximated to nearest quantization level. Then, if you observe the PCM output finally, here there is a different procedure we are going to use to observe the PCM output. So all of you carefully observe this. So here we have to consider any one of the input signal. Let us take the one place sine wave, and that one place sine wave is connected to here. And if you observe that in the CRO, that is the sine wave and some amplitude and frequency. Now, if you observe the sampled output here, and that sampled output will be like this, having number of samples. And if you observe the quantized output here, after this block, you can observe that there is a quantized output. Just the only difference is all the sample values are round off or approximated to nearest quantization level. That is only the difference between sampled output and quantized output. Next, when we observe the here, all of you observe what is the encoded output here. What is the encoded output after the encoder? You observe that all the LEDs are turned on only. That means it is not the indication of all ones. It is not the indication of all ones because when you observe the sample output in the signal, we have a number of samples are there. Based on the number of samples, each sample value or each quantized value is only encoded. That means here first initially at the first sampling time, one quantized value is passed. Only for that quantization only, there is some 7-bit of information is transmitted. That means for a first sample value or a quantized value, 7 group of bits are encoded. For the next sample or quantized value, next again 7 bits are encoded. Like that, 7 bits are encoded continuously, one after the other. This is not the indication of all ones. So because the number of samples are continuously coming as the input to the encoder, so it is continuously making the or encoding into 7 bits of sequence. So these sample values are continuously coming within a fraction of seconds because the sampling time used is generally in microseconds. So for every 1 microsecond, one sample value is coming. So within the fraction of microseconds, these LEDs are changing. That's why we cannot able to observe whether the LED is on or off. So for this particular sine wave as analog signal, if you observe this, this is what the observation of clock signal. Okay, what the clock signal. And if you observe the direct output for this analog signal, since the analog amplitude having number of samples, so we are getting a number of bit sequences, one after the other. So there is a large bit sequence is there. For example, the sample signal is having 1000 samples. For each sample, 7 bit of information. That is, for each sample value, 7 bits are transmitted. For all those 1000 sample values, 777 and so on up to 1000 times these 7 bits are transmitted. So totally 7000 bits are transmitted at the PCM output. So if you want to draw the pulse waveform for those 7000 bits, so that will be obtained like this. So it is a random representation of ones and zeros, having high and low pulses like this. Okay. So we cannot able to clearly observe how many ones are there, how many zeros are there, where the high pulse is there, where the low pulse is there. It is very difficult because the large number of bits are coming at the PCM output. So what will we do is we are going to observe only the encoded output only for one sample. Only for one quantized value, we are going to observe what is the encoded output. Now let us see how to take only one sample value. For that, instead of taking a sinusoidal signal, we are taking the DC signal. The DC signal will provide the constant amplitude value, whether it may be 3.2 volts or 1.2 volts, 2 volts, whatever it may be, you can change the value. So based on our input sample values, you can take any one sample value as the input signal. Only for that sample value, we are going to observe what is the encoded bit sequence. Then only you can clearly observe what is the PCM output. Now we'll see, instead of taking this a sinusoidal signal, we are taking one DC signal and changing the amplitude of the DC signal or a sample value. For each sample value, you can clearly observe what is the group of bits which are assigned at the encoder. So here I am changing the amplitude value, so you can clearly observe change in the bit sequence. Okay, you can clearly observe the change in the bit sequence. Is that right? So as a simple explanation, I am changing the amplitude value so that alternate ones and zeros are coming at the encoder output. So at this particular point, if you observe that for a random sample value, any one sample value if you take, that sample value is quantized to the nearest value, and based on that quantization value, based on this one quantized value, 7 group of bits are assigned. So what are the 7 group of bits assigned here? 1, 0, 1, 0, 1, 0, something like that. Okay. So if you observe, if you adjust some amplitude, perfectly you will get the 1, 0, 1, 0, 1, 0, 1, 0 as a sequence. This is only an example. If you change the input signal amplitude value, you may observe different bit sequence. It may be 1, 1, 0, 1, 1, 0, 1, 1, 0 also, depending on what the amplitude value are taken on the one sample. Then if you observe what is the output sequence, the PCM output, then you can clearly observe that 1, 0, 1, 0, 1, 0 waveform is okay. Now if you observe this PCM receiver, so it is a direct operation. Similarly, what I have explained in the time-division multiplexing, in this PCM also both the transmitter and receiver must be operated based on same clock. So here clock and clock pulses, clock inputs both are combined, so that both the transmitter and receiver sections are operated in a synchronized way. Similarly, ground also must be common for both the bits. So that's why here clocks are combined from transmitter to receiver. So if you observe the connections, how they are made, these clock pulses are connected to this point. So observe the video. The clock pulses which are there in the transmitter side, the same clock is applied here. So one is synchronized clock and transmitter clock, both are combined and applied from transmitter to receiver. So then only both the transmitter and receiver both are synchronized. If the both transmitter and receivers are synchronized only, then only we can get the reconstructed waveform perfectly. Now PCM output is directly connected to the input of the receiver, and similarly, as I already explained, both must be having common ground. Then both are having common ground. Now if you observe what is the decoded sequence, whatever the sequence we are used, we have produced at the output of transmitter, that is nothing but 1, 0, 1, 0, 1, 0 alternate sequence. The same thing is decoded here. Based on this decoded sequence, you can get the reconstructed original demodulated signal here. If you observe this point in the CRO, then in the CRO, this is what the decoded sequence. So in the CRO, I'm connecting this to CRO pin, CRO probe, positive and 0 to the negative. Now if you observe the output as a constant line. Why we are getting a constant line means, since we have changed the input to DC value, so only that DC signal is obtained as a demodulated signal. Okay, the same amplitude whatever you are given as the input, that same height or the amplitude value is obtained as a demodulated signal. But if you change the input signal from DC to analog signal, that is 1 kHz sine wave, then if you observe the demodulated signal, here I am changing the DC to AC. So sine wave is given as the PCM input. If you observe the PCM demodulated waveform, then you can clearly observe the demodulated signal is again a original sinusoidal waveform having 1 kHz frequency with some amplitude. Okay, so this is our experiment of pulse code modulation and demodulation. After doing the experiment, all of you should make some observations and calculations. The first important thing is all of you must observe input signal, sample signal, quantized signal, PCM output, and should calculate what is the signal amplitude and signal frequency, that is FM. Based on that, you should calculate what is the sampling time, how the sampling time is calculated, how TS is calculated. TS is calculated from the sampling clock, that is what is the time period of that clock is nothing but the TS. Based on the TS, we can calculate FS. And then we need to verify whether the sampling condition is satisfied or not, that is whether FS is greater than PFM or not. Next, observe the sample and quantize the signals in the CRO and identify how many number of samples are generated. If you observe that how many dots in the sample output, that indicates the number of samples. You can also calculate number of samples also. And observe the PCM output for one single input sample value, that is from DC signal in the CRO, and also note down the corresponding bits. And repeat the PCM output for different input sample values. You need to observe the PCM output not only for a single DC value, you need to observe the PCM output for number of sampling values, like 2 or 3. And observe the demodulated signal from PCM receiver and the CRO, and then calculate what is the amplitude and corresponding frequency. And again, identify whether the digital bit sequence is perfectly decoded in the PCM receiver or not. Okay, this is what the observations or calculations doing the experiment.
So this was all about the two experiments, pulse width modulation and pulse code modulation. What we have observed in the pulse code modulation here, we have seen the sampled waveform, we have seen the quantized waveform, quantized signals and the sample signals we have observed in CRO, and how analog message signal is converted into digital form. And we have also observed how PCM signals are generated, transmitted and received or decoded at the receiving side. And after that, we have observed the pulse coded modulation sequences on the CRM. So I hope you all have understood these two experiments and their related concepts. Thank you.